In our sky is this one, Betelgeuse. It's a red giant star. If you put it where the sun is, it would extend out to the orbit of Jupiter. It's enormous and very unstable. It's about to explode. This idea was supported by the fact that there were significant changes on the star's surface. In the end, the Hubble Space Telescope, humankind's watchdog in space, helped us figure out what was going on with this strange event. Hubble's views showed that the dimming of Betelgeuse was probably due to a large amount of hot matter being thrown into space. This material formed a cloud of dust that covered part of the star's surface, reducing the amount of light from Betelgeuse that reached us. It was thought that the dust cloud was made of very hot plasma that erupted from a large convection cell on the star's surface and moved through its hot atmosphere to the cooler outer layers. As it cooled, it formed dust grains, creating a cloud that blocked light from about a quarter of the star's surface. Hubble's ultraviolet light spectroscopic studies, which began in January 2019, were instrumental in piecing together the events that led to Betelgeuse's dimming. These studies showed signs of dense hot matter moving through the star's atmosphere. Several ground-based telescopes also observed the star's dimming in December 2019, particularly in its southern half. Initially, the material was brighter than the star itself, but as it moved outward and cooled, it turned into a dark cloud. The prevailing theory was that this outflowing matter and the resulting dark cloud were responsible for the star's sudden dimming. This explosion was truly enormous, placing Betelgeuse at the center of astronomical attention. The star ejected about 400 billion times the mass typically expelled in a normal coronal mass ejection. This material, estimated to weigh several times as much as the Moon, was a significant event for both Betelgeuse and our understanding of stellar processes. But what does such a massive explosion of matter mean for our understanding of Betelgeuse and supernovas in general? It has profound implications for our theories about supernovae. Red supergiants like Betelgeuse are thought to lose mass at a fairly steady rate before they explode at the end of their lives. However, the size of this ejection challenges this idea, suggesting a more turbulent and possibly unpredictable end-of-life phase for these stars. Could Betelgeuse be preparing for its final act, a supernova explosion in a few thousand years? New studies speculate on when this might happen, suggesting it could occur sooner than previously thought, possibly in just a few tens of years. Another important aspect of the Betelgeuse puzzle is the concept of bow shock. This massive star hurtles through space at about 67,000 miles per hour relative to the interstellar medium around it, creating a bow shock similar to the wave formed by a ship's bow. This effect occurs when the star's outer layers interact with the gas and dust in the space between stars. It's a beautiful demonstration of the star's activity and its interaction with its surroundings. The bow shock not only informs us about Betelgeuse's current state, but also helps us understand stellar evolution and mass loss. What about the star's past behavior? After the mass ejection, Betelgeuse's surface cooled and became less dense, indicating that the star remains unstable even years later. Hydrodynamic models show a link between the star's convective activities, the mass ejection, and subsequent changes in pulsation modes. This ongoing instability raises questions about the internal processes driving these changes and what their ultimate outcome might be. Additionally, Betelgeuse's mass loss rate is significantly higher than that of many other stars, suggesting a complex interplay of internal forces. The pulsation contributing to this mass loss is constrained by the continuous energy loss through shock heating and mass ejection. These observations indicate that Betelgeuse's life cycle is highly dynamic and not entirely predictable, prompting scientists to rethink their models of stellar evolution. With all these significant changes, one might wonder if Betelgeuse is about to go supernova. This question is of great interest to astronomers. The exact timing of such an event remains unknown, but the recent unusual mass ejection has shifted the discussion, leading some to believe the end may be nearer than previously thought. Theories are now attempting to determine what this massive loss of matter means for the star's health and future. While astronomers focus on Betelgeuse, the supernova SN 2023 EXF is also garnering attention and can be used for insightful comparisons. This remarkable explosion occurred in Messier 101, also known as the Pinwheel Galaxy, which is only 21 million light-years away. SN 2023 EXF, discovered in May 2023, is not just another supernova. It's the closest one observed in recent years, providing scientists with an excellent opportunity to study the star's final moments. The discovery of SN 2023 EXF was a cosmic coup. Kiichi Itagaki, an amateur astronomer known for discovering supernovae, first spotted this rapidly brightening spot on the edge of Messier 101 with a small 0.35-meter telescope. As soon as he announced his discovery, the astronomy community sprang into action. From ground-based observatories to the Hubble Space Telescope, telescopes around the world turned their gaze toward this new supernova. The race to monitor SN 2023 EXF's light curve yielded critical information about the explosion and the environment surrounding the dying star. Scientists carefully recorded SN 2023 EXF's behavior during the tumultuous month following its discovery. In just 5 days, the supernova brightened significantly before beginning a more gradual decline, dimming by 0.03 magnitudes each day. Spectroscopic analysis revealed numerous bright emission lines, indicating intense interactions between the expanding supernova shockwave and the surrounding gas. This wasn't just the death of a star, it was a massive star collapsing under its own gravity as its nuclear fuel ran out, resulting in a spectacular core collapse supernova. What's particularly intriguing about SN 2023 EXF is the dense shell of gas surrounding it, which made it more difficult for the shockwave to escape from the star's core. Two possible explanations for this dense material are either a strong, steady wind blowing material off the star before the explosion or random eruptions that expelled material into space. In either case, the star is believed to have lost up to a solar mass of material in the last 1 to 2 years of its life, indicating its final moments were far from peaceful. The primary goal of research now is to identify the progenitor star of SN 2023 EXF. Researchers have used a variety of methods and statistics to suggest a likely candidate, a red supergiant. By studying the specifics of SN 2023 EXF's explosion, such as the characteristics of its progenitor star and the processes leading up to the final blast, astronomers can refine their models of stellar evolution and supernova mechanics. These new insights directly inform our understanding of Betelgeuse's current state and how it might end up going supernova. They offer a better sense of the signs to watch for and how to interpret the complex behaviors of massive red giants. But when will Betelgeuse become a supernova? Researchers at Tohoku University suggest that Betelgeuse may be in the carbon-burning phase of its life, a stage stars typically go through before they die. Hoki Seo, who leads this work, believes that the star's core might collapse a few tens of years after its carbon supply is exhausted. On the other hand, scientists at Hungary's Konkoly Observatory think Betelgeuse is in an earlier helium-burning stage. While there are differing opinions, most agree that Betelgeuse will likely be the next supernova in the Milky Way. However, this event might not occur for another 100,000 years. In the past, observing supernovae has provided valuable insights into the death of stars. The first known record of a supernova was made in 185 CE, noted as a bright star that disappeared from the sky after 8 months. Since then, many significant supernovae have been observed, including SN 1054, which created the Crab Nebula and was visible during the day for 23 days. The most recent supernova observed in the Milky Way was SN 1604, studied in detail by Johannes Kepler. More recently, supernova 1987A in the Large Magellanic Cloud was observed just hours after its light reached Earth. It was the first supernova observed through neutrino radiation and across all electromagnetic spectrum bands. These observations have been crucial in developing accurate models of supernova behavior and understanding their role in star formation.